Okay, everyone, so let's start. So in case you haven't picked up already, there are three handouts out here, so make sure to collect them. So welcome to EE16 and kind of the cross-listed CS51. You want to be spending a quarter with me, so my name is Manish Srivastava. I'm on faculty in both electrical engineering and in computer science. So this is a cross-listed course. And today's agenda, we are firstly sort of going to go over some of the logistic issues, grading and stuff like that. And then we are going to dive right into the first chapter of the textbook. So let's start down, and feel free to sort of interrupt me as I go along. I'm going to also sort of ask you guys questions. So okay, so this slide, and you all have copies of it, has information to reach me. Probably the best way to reach me is to actually post onto Piazza. And all of you should have received email, both from me directly as well as from Piazza, about using that as the forum for us to communicate. So that's the best way, but in case of an emergency, you can always call that phone number listed out there, or contact my assistant, Sandra, to try to reach me. And we have two TAs, Wei Wu and Tianyu Li. They're very experienced. They actually TA'd this class last time also, last quarter as well, under a different professor. So they're very familiar with the course material out here. And again, their email information is out there. Perhaps the best way to reach them also is, again, to use Piazza. I'm going to talk about what Piazza lets you do or not, in case you're not familiar with it. Schedule information. So I guess more important one out here is the office hours. So I'm going to hold 3 office hours of 1 hour each, and then the TAs are going to hold a total of 4.5 hours of office hours. So basically, pretty much every day, every day you can kind of contact one of us or the other, and we have staggered them enough so that hopefully you will not have consistent class conflicts. In case it turns out that some particular hour is very bad, we don't see students coming in, we'll probably kind of revisit that. My office hours are going to be in my office, 6730E, Bolter Hall. It's on the south side, south hallway of the building. And the TAs are going to do it in Engineering 4, the EE TA office, basically. So we are going to, you're going to be meeting them there. Outside these office hours, you can always sort of contact me or the TAs, and we'll try to help out to the maximum we can in arranging some other time for you to meet us. Besides these, we'll probably, closer to the exam times, you're going to also hold weekend office hours or something like that to take on additional questions. Okay, so what is this course about? Its title is Logic Design of Digital Systems, and there are kind of a couple of things that come up out here. One is digital systems. So anyone wants to mention what is a digital system? Come on there. Anyone here? What does digital suggest? Ones and zeros, okay. What else? Someone said computers, okay.
Discrete packets of time.
Say it again, please.
Discrete packets of time.
Discrete packets in time, okay. Discrete instance of time, okay. What else? So we heard 1, 0, or if you were to generalize it, instead of a continuous value, we are discretizing the value, and then back there, discretizing the time. And both of these are actually important aspects. So in digital systems, what we'll see is that the values are discretized, so they come from a finite set of values, and time is discretized, as in we worry about things. In most digital systems, we worry about things that are happening at some time, special time instant, and we'll see the notion of clock. So every time the clock ticks, that's when things happen, and in between, not much. As contrast it with kind of like when you, in physics courses and all, you see sound waveforms and all, they have continuous values. So between the two amplitudes, they take any arbitrary value, it's a real number, and they are continuous in time also, right? So equal. So digital systems kind of seek to discretize both, and a lot of time we'll start out with discretizing value, and then much later in the second half of the course we'll also look into when time gets discretized with this clock that we talked about. Second thing out here is logic design. So logic is more of a mathematical term. That is, in effect, you can say that we are going to systematically come up with the rules of the game out there. Okay, so what are the basic operators? How do we combine them? Much like when you study algebra or calculus and whatnot, we start with some basic axioms. We kind of build up more complicated things on top of it. It's the same thing out here. So this is kind of, if you may, the math of digital system is one way of kind of looking at it. So logic design of digital systems. Some of the questions that we will try to get a sense of how to make complex digital systems. Computers being a great example, they are mostly digital and they are pretty darn complicated. But more importantly, we're going to look at how to make these things from simpler stuff. One of the things that makes engineering work out well in real life is that when taking on complicated problems, we break it down into simpler pieces. We try to understand how to design that simpler piece and then put it together. Digital systems are no different. We are going to see simple stuff and we are going to look at how you can combine them together into making more complicated things. Obviously, since the name of the course is logic design, so we are going to go into some of the more theoretical stuff. But along the way, we'll also try to give you a practical perspective. So kind of how to design, using these principles, how to design useful things. So that's one of the things we are going to try to do, both through the lectures, you'll see some lab type, design type homeworks that we will have. Designing digital systems, much like engineering, I always think of it like art. As in when you engineer something, it's very important that it be elegant, it be nice, it should be something which is well designed. And same thing is true for digital systems. We are going to look at how to do good digital system design. Good design is important because when you engineer something, the system still will live on. Someone else has to maintain it. Someone perhaps has to recreate it. Maybe you have to design the second version of it. So all of these things are facilitated if you design well, if you design in a fashion which is easy to understand. And this is not true just for digital systems, but pretty much of engineering. What we will not learn about. So we'll not learn about how the primitives, which we call as logic gates, how they are realized. They could be realized electronically using transistors. Long ago, they used to be realized using vacuum tubes. In recent years, people have tried to realize them using chemical molecules, using quantum stuff, using biological cells. So the concept of digital system is really independent of electrical or electronic thing. You can imagine these things being realized mechanically, biologically, chemically, optically, in many different ways. So we're not going to worry too much about the specific realization of the digital systems. We are also not going to worry about how they are manufactured. There are, again, courses for all of these things, particularly in the EE side of things, as well as we will not worry much about the software that runs on these systems. That's what you'll learn in follow-on courses in computer science. So this one really, we're going to focus really on digital systems, kind of their theory and somewhat in practice, but do it in a way which is more general than just electrical digital systems. So after you take this course, presumably most of you are first or second year students. There are many follow-on courses. There is a lab, which is where you actually work with electronic realization of these digital systems, EEM16L. There's computer architecture class where you kind of go into how to actually make kind of decent computers, how they're organized. There are digital design project courses. There are digital circuit courses where you go into transistors and all, and likewise many other courses which kind of overlap with that. So this sort of lays the foundation for a lot of follow-on coursework that you would see. Textbook. So we are going to be using this book, Daly and Harting. Should be in the bookstore. It's on Amazon, a bunch of places. The lectures are going to hew fairly closely to the book, although I do have additional material from places, so slides are going to capture that. This is a relatively new book. In fact, the first time we used it at UCLA was last year when I taught this class a year ago. At which time it had just come out. So still it's in the first edition, so there are typos, there are errors. We kind of gained from the experience the first time around, things that worked, that didn't work. So as you kind of go along, you'll see there is some stuff there which is not quite right, but overall, I think it's one of the best textbooks around. One thing, the way this book is written, is it actually uses a language, a programming language called Verilog, which is used to describe hardware. This is how things are done in the industry. So throughout the book, there are examples in Verilog. We are not going to use Verilog. So anytime you hit Verilog, just skip over that. You're going to see Verilog in that lab course later on, as well as many other courses here. But this course, we are going to skip over that part, and just kind of use the book for the conceptual part of the digital logic. The chapters that we will cover, so I've kind of listed them out there. So the book obviously is designed for a much longer course, so we are going to do a subset of those. You'll see at the bottom I've marked a couple of things, a few things as tentative, so we'll see how it goes along with the pace and all. We may hit some subset of that material. But basically what I've listed out here are the chapters will follow, but not in sequence. So I've a more detailed schedule in a later slide where kind of I lay down which day what chapter we'll cover. Online resources, so we'll be using CourseWeb for most stuff. Occasionally you may encounter links which lead to password protected files on a different web server, in which case the ID and the password are as listed in this slide. Grades would get posted on my.ucla.edu, and online material will certainly put the slides. I also try to record all my lectures, so after delay of a day or two, a file with sort of slides and audio get put. This time around I'm planning to post it onto YouTube, so you'll see a link to that. Now having said that, I don't promise it would be there because occasionally the software crashes and all, and so if any of the lecture doesn't make it through, don't blame me. It's basically purely on a best effort basis, but it does serve a couple of useful things. I think the primary thing is closer to the exam, you can always go back and kind of see what happened. Unfortunately, what doesn't get captured is what's on the blackboard. So what I instead do is I have this little tablet out there and I draw on the slide. So to the extent possible, I'll try to do that. But occasionally we'll have to kind of use the blackboard, in which case that material doesn't get captured. Also, problem with this is it captures what I'm saying very well. Questions that students ask don't necessarily get captured very well. So it's not perfect, but at least of some help. But again, sort of, I don't guarantee that any of the recordings would necessarily get made, but in case of snafus. Also, homeworks, handouts, exams, solutions to exams, and all will kind of post it. Slides in particular. So today I distributed all the slides because the first lecture. As I noted already on Piazza, for future lectures, I will not do that. So you'll have to print it out. We'll put the slides up 24 to 48 hours in advance. You print it out. Many students like to bring them on their iPads or whatnot and just annotate things. So whatever works for you. The slides, there are 2 versions of the slides on the website. One version says with animation, the other says without animation. Without animation doesn't show all the animation steps. Occasionally I use animation, so whichever one works for you. If you are printing it out on paper, it might be better to print multiple slides on a single page just to save some trees. Don't ask me to generate that PDF. Every printer driver has that capability. You go to the layout and select 6 slides to a page or 4 slides to a page, so you can just do that yourself. The PDFs are 1 slide per page. So again, you are responsible for downloading and printing. Piazza. How many of you have never used Piazza? Okay, fair number. So this is a commercial service which many courses at many universities are beginning to use. What does Piazza stand for? Anyone? Italian? A meeting place. Okay, so plaza, right? So Piazza is kind of very well done, or at least I feel that way, and I think feedback from my other courses have been pretty good. It's a very well done forum specifically targeted for coursework. So what Piazza let you do is essentially kind of do a pseudo real-time kind of class discussion. It seeks to emulate that. And you can post questions. You can post questions one of 4 ways. You can post a question with your name attached and broadcast to everyone. You can post your question anonymously, broadcast to everyone. You can send a private question which just comes to me and the TAs with your name attached or anonymously. So kind of four ways you can go, whatever kind of works for you. Moreover, so firstly, I would say, if at all possible, if the nature of question is technical, broadcast it to everyone with your name attached so that others can jump in and collaborate. So in that case, it begins to act like a wiki. Other students can collaboratively edit the question, enhance it, even answer it. Oftentimes, before I answer, some other student kind of answers that. So it becomes a very nice collaborative learning kind of experience. So give it a shot. I'm pretty confident you would like it. Oftentimes what happens is by the time I come to look at it, someone has answered, and then I'll just endorse that this is the correct answer. Either I or one of the TAs would sort of end up doing that. You could also edit, modify, and also it's a very nice system. So we'll use that. So specifically what it means is we'll not be using CourseWeb doesn't really have anything equivalent out there. CourseWeb does have an announcement capability, but instead of fragmenting things, we're going to put everything on Piazza. So this would be the primary place for you to get information. You could either log on to the website, or they also have apps for mobile phones and all. So it can push, notify, all sort of modern stuff that CourseWeb lacks on this regard. So again, Piazza. I had signed up all of you, as in all of you were enrolled, but you still need to activate your account. And I think last I noticed some 15, 20 students had not activated. So see if you have an email from Piazza. If not, go to piazza.com and look for this course and just make sure to activate your account. It could be the email I used is the one which is on the registrar record. Maybe that's not an email you regularly read. If that's the case, then you might want to sign up under a different email account. Anyone did not get an email from Piazza? Okay, so I think we are good on that front. So we can ignore this. That's the sign up URL. And eventually, kind of, it's your responsibility to make sure you are signed up. One other thing, in Piazza, you can set it up so that it can either push the announcements and post things immediately to you, or in digest every couple of hours, or in a daily digest. I think everything being pushed at you instantaneously could be very burdensome. At the same time, doing it once every day is too slow, because if a homework is due, we are sending you updates. You get to see it only at night, might be too late. So sort of set the frequency fast enough so that you're on top of what's going on. Closer to deadlines, there's a lot of back and forth that happens, some ambiguity in some questions, someone asks something, so you'll miss out on all of that. So again, you should take care of setting things accordingly. Any questions? Okay, grading. So we'll have 4 problem sets. They will account for a total of 16%, but not equally weighted. These would be conceptual problems based upon the lecture, so roughly speaking, 1 every 2 to 3 weeks. We'll have 4 design assignments. One which is actually due this Friday. It's already been handed out on Piazza with a notice, with a link. It's more of following a tutorial, so it's a way to force you to kind of install the necessary software and all. So I'm going to describe it in detail. These design assignments are going to account for 33%. We'll be using a tool called Logisim. It works on Macs, it works on PCs, it works on Linux machines in case you're using one of those. So it's pretty well supported on various platforms. It does have some bugs, but it's pretty much the best free tool of its type which is out there, and we use it in this class, in all sections of this class now. So as you can see, more emphasis on design than on the plain problem solving in terms of homework. By the way, the design assignment, the way it would work is that the first 3 design assignments kind of build up your expertise, and the final one, which would carry bulk of the weight, is going to be kind of a mini project where you're going to make something more complicated. So that's how the design assignments will proceed. We'll have a midterm during week 6. Actually, it would be on February 5th. I have the date in the calendar, so maybe the week number here may be possibly wrong. And then we'll have a final. Both the exams are going to be open textbook and 1 cheat sheet of a page, 2-sided, single page, where you have to write things in hand. So you cannot photocopy stuff, you cannot bring lecture notes, but you have access to your textbook and 1 cheat sheet. Both the exams are equally weighted. They are both 2 hours, so midterm is actually 1 hour 50 minutes because that's our lecture slot, whereas the final would be actually 2 hours. The final is on the Friday of the finals week at 8 a.m. So early morning. Then finally, I really want to encourage you to participate. So in multiple ways, and therefore what you would see is that I've allocated actually a fair bit to participation. Now this is where Piazza helps me. So even though you can remain anonymous, what I do get to see is how much participation different students had, how many times they asked a question, how many times they read responses to a question, how many times they responded to a question, how many times they even logged in and all. And I'm going to be giving a participation score based in part on your Piazza participation, in part on office hour participation, as well as during lectures. So 6% is a fair bit of score. So don't ignore it. Oftentimes I have students who the only time I see them is during the exams, and I think that's certainly something to be avoided. So that's almost like free scores for participation, so try to avail that. Any questions on grading? Okay. A bit more on the grading. So I really want to encourage you to focus on learning what is really kind of a foundational topic for a lot of your follow-on coursework, whether you are in CS or EE. The scores, the absolute scores don't really mean much because an exam may be hard or a homework may be hard and then everyone kind of blows it. So it's not like 80% is B and 90% is A or anything like that. It's I kind of follow somewhat of a hybrid model. So the scoring is relative, but I do shift the relative grade up and down based upon how previous iterations, students in previous iterations of this class have performed. So there is sort of an absolute sense because sometimes a class is really very good, sometimes an overall class is on the weaker side, so we do normalize for it. but otherwise, sort of, it's the curve is within the class. So this way, I get to kind of normalize for some assignments, which may turn out to be more challenging than perhaps I thought they might be. So dominantly comparative achievement, but the overall grade curve, we adjust it based on historical performance. Grading by TAs. So some of the material might be graded by TAs and some by readers. Readers you will not have any interaction with. So in case you have complaints on grading there, you meet on our TAs or me. Material that's graded by the TAs. The policy is I'll not second guess the TAs. They are part of the instructional staff. So any concerns first you have to resolve directly with them. Only if then there is still some lingering snafu that I would sort of come in. But generally, TAs are very competent senior PhD students. They know as much about this topic as I do. So I'll sort of respect their judgment in this regard. So your first line of defense in case of any problem with grading is to go to the TA who graded it. Okay. Format of exams. Midterm exam, an hour, 50-minute. Textbook plus one original handwritten cheat sheet, single page, a single two-sided page. I find the act of preparing the cheat sheet to be a great preparation. So that's why I kind of allow that. You cannot photocopy. It has to be kind of handwritten, your original work. Final exam, same way. The only additional thing is final exam will focus on the latter part of the course. Now, having said that, the way the material is, the latter part of the course builds upon the first part. So even though there may not be an explicit question about the early part of the course, you will still need to know and understand that material in order to be able to do the second part of the class. So final is not cumulative, but does depend upon the knowledge from the first half. No blue books, so all homework and exams and all, there'll be space for you to answer, and that's where you have to answer. If you use any other sheet, we will not grade it, and we are going to be very rigid about that. So, and this applies to homework also. There is plenty of space in the homework booklet, and you have to answer there. Homework logistics. Late submission policy, no grace period. So if you miss the deadline, zero score. Unless I decide to change the deadline uniformly for the entire class, which on occasion I may have to do, although I don't expect really this time around. But like in case there was some snafu with the tool, or maybe there was a mistake in the way we presented the question or something like that. Homeworks may carry different weights towards the grade. So even though they will add up to the stated grade, the distribution. So every time we hand out a homework, we'll say how much of the course grade it would account for. Problem sets, you are responsible for downloading and printing them. We will not hand them out. Again, we'll just post the link. We'll announce on Piazza. You go ahead and print it out. If we do an update, you will announce it, and then you can re-download. So like, for example, if there's a typo or some error. Again, you will have to answer in the sheet itself. Submission times would be aligned with one of the office hours. If you cannot make it to that office hour, then you can either arrange to meet us separately, or you can go and visit Sandra Bryant, my secretary, and hand it to her. But when you hand your homework to her, please make sure that she puts a timestamp and signs it, okay, so that you know, so that there's a record of when you submit it. And the way you are going to submit stuff is via CourseWeb. So you're going to upload the files out there, and we'll just download things from there. Logisim. So I mentioned this earlier as part of the design homeworks. So this is a tool which lets you design and simulate digital logic circuits. So kind of the screen is shown out there. It gives you a library of parts. You use those parts to create digital logic circuits, and then you can simulate them. That is, you can give them input, see what the response is, and see whether the circuit is working correctly or not. You should download it today. Very important for you to become familiarize yourself with it. In fact, we have a homework which is due Friday morning. It will work on any machine, but you will need Java installed on your machine. If you have a Mac, it comes with Java. If you have Linux, it usually comes with Java. If you have Windows, you'll have to download Java, but it's quite possible that you may have previously downloaded it because a lot of stuff uses that. You will need Java 5 or newer, and you can download it from java.com. So quite important, but the tool otherwise works pretty robustly. And then either from the Logisim's website or from within the program by going to the help menu, you should read the beginner's tutorial. It's called the Guide to Being a Logisim User. And you have to walk through the tutorial and you have to submit your tutorial files. So there are more detailed instructions in the homework announcement. So very important that you do it. And it will probably take you maybe 3-4 hours. There's a video and all what that have attached, depending upon your kind of prior level of expertise. When you come during discussion section this Friday, you would have submitted this homework. So that means you would have Logisim installed. You would have gone through the basic tutorial. We would like you to bring your laptops because the TAs are going to go through additional Logisim thing. And in general, you should bring your laptop to the discussion sections because we'll often demonstrate stuff using Logisim. It's a very powerful tool and you would need to have ready access to that. If you do not have a laptop, I believe you can rent it out from the library on hourly basis, so arrange to do that well in advance. So quite important, this course will depend very heavily on Logisim, so you need to set yourself up. Any questions at this stage? Go ahead.
The tutorial is supposed to take us 3 hours?
You know, if you're totally newbie in terms of computing. Otherwise, maybe half an hour. So it's pretty simple, okay? Huh? Okay, yeah. I have students get hung up on Java installs and also I'm being very conservative out there, okay? But it's really very rapid. The video itself, if you just follow it very quickly, you submit the file, that's it. But again, the intent is not so much to teach you anything in that tutorial, but force you to install stuff so that you come ready, good to go during discussion section. Okay, so that's Logisim. Tentative course schedule. So you probably already saw the announcement. I have one missed lecture this quarter, and that happens to be this week. So we're going to do a substitute, perhaps a weekend review session for one of the exams later in the quarter. So a good way for you to make use of the next lecture slot might actually be to go through the Logisim stuff and kind of just take care of that. Then I've kind of outlined the rough plan based on what I had done last time around. So hopefully I'll be able to hew pretty close to it. Midterm is on February 5th. It will be proctored by the TAs, but I'll hold review session the evening before for you to go over it. And more detailed schedule. So sort of try to plan things out. Okay, cheating and plagiarism. So I'm sure you're kind of aware of all the standard UCLA policies and all. Since a lot of material out here is take home, particularly design assignments and all. So bottom line is that anything which is individual, you have to do it by yourself. That means not only not collaborating with others on that, but also not hunting on the web to find solutions and all. It kind of defeats the purpose. One of the nice things about design assignments is that there are often multiple different possibilities, and it's a dead giveaway. Oftentimes, when I find solutions which replicate the same weird mistake, which is kind of a dead giveaway that there was collaboration. And so try to avoid it. If you are in doubt on what is okay or not, send me a private note on Piazza. For many things, it's okay to discuss on Piazza, like if you have a doubt about the question, you can kind of do it. You can discuss among them. So I guess in politics, as they say, it's the hiding often is worse than the crime itself. It's kind of the same thing out here. If you're open about it, you have a plausible excuse. If, on the other hand, the first time I learn about collaboration is when I'm grading stuff, then that doesn't look good. So please don't engage in that. But if you do decide to, we'll follow just a standard school practice, which is will not give you a grade on that piece of work. I'll forward it to Dean's office, which then forwards to the campus level, and then they kind of decide what to do. Important to-do list. Download and install Logisim. Read the documentation. So even though the homework due on Friday only asks you to go through the basic tutorial, but also read rest of the document, at least glance through it and all. It's a reasonably friendly tool, and the documentation is pretty well written. Again, it's accessible through the help menu within the program. Make sure you are signed up for Piazza. And that means activate the account, go there and make sure you set your mailing preferences so that you get the mails frequently enough. Download and print slides prior to each lecture so that you can take notes, or you can bring your laptop or tablet. Slide annotations and on the fly stuff. So I'll always post kind of a modified version of the PDF, which may have any annotations that I may make using the tablet out here. You're highly encouraged to read the relevant sections of the textbook, if at all possible, prior to the class, certainly after the class. It would make comprehending the lectures a lot easier. And we'll be making use of Logisim a lot in discussion section and occasionally in the lectures as well. So having your laptop handy would be usually quite beneficial. And we cover a lot of materials. The material we cover is usually a semester-long course. If you look at schools like Berkeley and USC and all semester-based schools, they cover the same material in 14 weeks or 15 weeks. We have to cover it in 10 weeks. So it's, in terms of real time, it's a lot more highly paced. So missing a single lecture here is a lot of falling behind. So try not to. I try to put out the recording so that you can make up if you do happen to, but it's no substitute for being in the lecture out here. Some other announcements. So this week, I will not have my Wednesday office hour, again, for the same reason why I'm missing the lecture. So instead, my Friday office hour will be a 2-hour long office hour. So I'm making up for that. So by that time, you would have also gone through discussion sections. So you can ask me any questions about that. And the second thing is no lecture on Wednesday. So instead, make sure to go through the design assignment 1, which is due 9 a.m. on Friday, January 10th. This is a typo. So I get to try my... So on Friday 10th, 9 a.m. it is due, and then sort of a sketch of the instructions are out here, but you go to that link that I have up there. It will take you to a Google Doc, and you would see the more detailed instructions there. If any of you already downloaded and printed this homework, the TAs have modified the submission instructions a little bit this morning. You'll have to do it again. I'm using CourseWeb for the first time, so they made me aware of some additional capabilities. So they are modifying it. They probably already have modified it. So you would need to download it again. If you didn't already print, don't worry. Okay. So any questions at this stage before we kind of dive on to the main lecture?
You curve downward.
What does that mean?
So like, if everyone gets a high grade, you curve downward to the low grade.
If everyone gets high grade, firstly, it never happens. Law of large numbers. So now it's a good question. If everyone gets an identical grade, I don't know. I'll probably see how it stacks up against some previous offering of the class. But Will never happen, trust me. Any other question? Honestly, I don't even know what you quite meant, but look, we are not out to destroy your grades if that's what you're doing. Okay, so go ahead.
Has it ever been like necessary to reference the textbook for an exam? Like actually go into it so I look at something?
You know, honestly, I don't think so, but it gives students some comfort level to have some material out there, so I let it. Okay, I mean, to be honest, students who need to refer to the textbook probably didn't study to begin with, okay, because if cheat sheet suffices for key concepts, is how I put it, occasionally there are some problems which you found particularly tricky and also jot down the tips on the cheat sheet. I think that works much better. Any other questions? Okay, so we are going to move to module number 2. So, digital abstraction or representing information digital. So we saw that earlier on that digital systems, we kind of that it requires discretizing values, it requires discretizing time. This thing is about really kind of going into that, in particular discretizing value. Okay, so the material here is basically chapter 1. And actually the next module also largely focuses on that. Okay, so what we are doing in this course is really, in effect, designing a type of system. And engineers deal with systems all the time. This building is a system, a car is a system, a computer is a system. They're all systems. And a system in a very abstract way is something you're designing which takes some input and produces some output. That input could be a spoken command, output is a transcription of that. That's a speech recognition system. Input could be an image, output is a list of objects in that image. That's the image recognition system. Input could be a text file with a word in every line. Output is the lines sorted in dictionary fashion. That's the system. So, and depending upon your discipline, we kind of design these systems differently. Civil engineers do a different thing than computer engineers, than mechanical engineers, and so on and so forth. These signals, which are going in and out, and the system itself could be realized in many ways: electrically, chemically, mechanically, pneumatically, with kind of air pumping and all, optical stuff, many different ways. And I guess in electrical engineering, we are more fond of electrical and optical stuff. If you go to chemistry department, they are working on chemical computing. If you go to biology departments, biological computers are the rage. If you go to physics department, quantum computers are the rage. And they all kind of use some physical phenomenon to represent values, and they design a system which outputs those values in some particular shape and form. Our particular interest is going to be on, obviously, things which are digital. The system itself could do many different things. So some systems are designed to store stuff. They remember things and they spit out things later on. Some systems immediately act upon them. Some systems just are spread over large distances. So they take their input at one location on the planet or the universe, and they spit out the output at some faraway location. So systems are designed to communicate, to store, to process, to make sense out of input, all sort of different things. But they're all systems. So input, something happens, output. Special case, digital systems, where the input signals and output signals are discrete valued. So discrete valued, if you go back to your math, the difference between real numbers and integers or whatever, sets of values, finite set of values. It's the discrete valued input signal and discrete value output signal. And to process these, they are done using the digital systems, because digital systems are designed to handle discrete values. So let's take an example. For example, a possible value may be open, close. So it could be my system is designed to detect the state of a doorway, whether it's open or closed, and based upon that, ring a buzzer. So in that case, the output is buzzer on, buzzer off. Input is door open, door close. I may have some other possibilities, like for example, maybe the input is set of words drawn from a dictionary. Output is those words output in a sorted order. Input could be letters of alphabet, numbers, a bunch of arbitrary symbols. Basically, any one of these possibilities kind of is equally valid. But the key thing is that the input and output are coming from a finite set of values. That's what makes it different from real numbers. If I do need to represent real numbers, we are going to discretize them. So for example, we may say that, I'm only going to represent real numbers in a particular format, like for example, to a certain number of digits before the decimal and certain number of digits after the decimal. That limits the set of choices I'm allowed. So I can discretize continuous valued things by putting them into bins. So for example, let's say height of people. So our height is a real number, but when we measure it using a scale, we round it off to, let's say, nearest quarter inch or half inch or whatever, and then that now becomes suddenly a discrete valued thing. So we are always kind of end up discretizing things anyway, so this is not that big a deal. And by having a large enough discrete set, you can represent sort of even continuous things very, very accurately. But more to the point, digital systems process at the input and at the output values drawn from some finite set of discrete things. A special case. So in response to my question very early on, what is digital? Someone said 0, 1. So as you can see, the previous definition we have, it's not just limited to 0, 1. These are all digital. A special case is when we are limited to 2 values, and that's called binary. So literally, binary is 2 values, but it doesn't need to be just 0, 1. It could be 2, 3. It could be true, false, open, close, dark, bright, whatever. Short, tall, heavy, light. All sort of possibilities around there. But the key thing is it's 2 values. A very common one, particularly in computing, is that we call one of them to be 0, the other to be 1. Which one you call 0, which one you call 1, depends. But it's very commonly, we kind of do it this way, but the main point is 2 values. The reason 2 values is good is because we know how to design and manipulate and kind of physically do things which are 2 valued very easily. For example, a switch is open, close. An electron has 2 states in a particular orbital, up or down. Light may be on or off. So there are a lot of things in physics which are inherently 2 valued, and therefore it makes us very easy to kind of deal with them. Another advantage of 2 valued is we don't have to guess things. So like for example, take my light example. I said on, off, 0, 1 is very unambiguous. If I start worrying about how bright the light is, now you are into the real number domain, analog domain, and then measurement becomes hard. Any noise in your measurement could affect things. So analog stuff tends to be less robust as a result. 0, 1 we can do very easily in a variety of ways, electrically, optically, mechanically. In a mechanical thing, it could be some sort of a lever which is in one position or the other. So binary is very attractive for a variety of reasons, so very commonly used. But having said that, not all digital systems are binary. There are digital systems which are designed using more than 2 states as well. In fact, some of the early digital systems had multiple states. One of the very first uh, computer was something called the difference engine. Anyone heard of it ever? Difference engine. Back in I think 1600s, 1700s, Babbage, scientist in UK, he made a mechanical computer, and it was digital, except that the discrete values were coming from the teeth of gears. So gears has finite number of teeth, so it's digital, but it's not binary because they have many teeth in a gear. So mechanical.
When you say digital system, is that a property that's assigned to a system or something that's distributed because of
It's a property we assign to a system. So it's an excellent question. It's a deeper question, perhaps. So let's take an example. Let's say I decide to use electrical voltage, a system which is operating on electrical voltage. Typically, what we do is we'll say values, let's say below a certain voltage, we'll call them 0. Values above a certain voltage, we call them 1. That's the meaning we ascribe to it. Underneath, the signal is actually analog. So that's an example where it's not intrinsically digital, but we are treating it digitally. So we just took a real number line and we called some region to be 0, some region to be 1, and perhaps some other region to, it should never be there. Okay. There are other systems which could be intrinsically digital also in normal operation, like the electron example I had. Okay, the spin of the electron is up or down, there's no other possibility, just from laws of physics. But more generally, you would see that underneath the system is actually continuous. We ascribe certain values to be 0, certain values to be 1. Any other question? Could anyone give me an example of some other physical modality which is intrinsically digital? Just exists in a finite number of states. I think phases of moon is, okay, so it depends on how we define it, but it's kind of continuous, right? Always changing.
alive or dead?
Huh?
Alive or dead?
Alive or dead? Yeah, that's unless you believe in Schrodinger's cat. Anyone heard of it? In which case you don't know, but yeah, alive or dead. Perfect. How about things which are deep down continuous, but we ascribe a digital interpretation to it? So we talked about voltage is one. Think of something. I'll try another. Chemical concentration. Okay, chemical concentration. In fact, that's how our brain works, right? I mean, when you read in biology, when you kind of study potentials and all, right? I mean, basically it's based upon the sodium ion channel, the concentration builds up at some stage, things flip. So that's an example where it's an analog phenomenon, but then it's firing or not firing. Okay, so there's a threshold out there. Any other example? Something which is continuous, but we think of it digitally. Huh? Time, yeah. So it's kind of interesting though. So you're right, time is continuous, we discretize it, but actually deep down time is still quantum. So it's discretized. So it depends upon where you're looking at. Quantum unit of time is 10 to the power minus 43 seconds or so. So time advances, but you're right. Huh? Growth, okay. Yeah, I guess, I mean, we discretize height into tall, short, medium height, so those are possibilities, right? I mean, we ascribe them. Healthy, unhealthy, medical stuff is littered with these examples, right? I mean, all our readings and all, they're continuous valued, but they're divided into normal range, above normal, below normal, right? I mean, so we discretize it. So many examples where continuous phenomenon, we kind of discretize them for sake of ease, sake of convenience. So when we have systems where we have two states, and particularly when we label them 0 and 1, then we call them bits. Analogy with digits, and that's what much of our electronic computing is based on. So now, several challenges arrive in this thing. So when it comes to physically encoding discrete values, if the physical quantity is also discrete, like the state of electrons, spin of electrons, that's easy. Or our fingers, we are a discrete number of fingers in our hand. The gearing in the teeth of gears, that's what that very first computer, a mechanical computer, was like that. So that's the easy case. We can take a phenomenon which is inherently discrete and then just kind of label them accordingly. So that's easy. What if the physical quantity is continuous valued? Light level, sound level, chemical concentration, bunch of things that we were discussing a short while ago. So what we do is, much like I was answering in response to this question, we designate some ranges to be 0, some range to be 1, and something else to be out of bound. So in this case, what you would see is that we have kind of, we have taken the voltage range, we have defined a range for 0, which is this blue colored one, a range for 1. So if the voltage is in this upper blue range, we'll call it a 1. If it is lower than Vmin or higher than Vmax, then we are in territory where the circuit can get damaged. So we should never be there. And then in the middle is an ambiguous thing. It's neither 0 nor 1, but we have put in a gap. And we'll see the reason behind this gap in a short while. What you would see in this numbers below is how a typical example of values coming from a particular semiconductor technology, something called 2.5 volt LV CMOS logic. But what you see out here is that in this one, values between 1.7 and 2.5 volt are treated as logic 1. Values between minus 0.3 and between 0.0 and 0.7 are treated as logic 0. And in between are treated as no man's land. And we'll see kind of the reason behind that very shortly. So that was the first challenge, that how do we represent them physically? If physical stuff is already discrete, great, our job is simple. If physical stuff is continuous, we are going to discretize it. We are going to define sets of those continuous values to map to our discrete values, 0 or 1 in our case. The other part which comes up is, what if what I want to represent has more than 2 states, right? So for example, let's say I want to represent the 10 fingers on my hand. So clearly a single bit is not enough. It's not simply a case of 0 and 1. And this problem, obviously, in general, we face a lot of time. We may have a finite set, but that set may have more than two members of the set, but we are trying to represent them using bits. So easy case, if information is discrete and the number of distinct values of information is the same one that we have in our signals. So if I am representing a set with 10 distinct values and I'm using the fingers of my hand to represent them, then I have a one-to-one mapping. So it's easy to do that mapping. But if what I am trying to represent has more values and my computer has fewer states, let's say a binary computer, then I have to do some additional work around it. So let's take example. So the simple case, I'm trying to represent the state of a door. Door is closed or open. That's what I want to represent. So I can designate one of them to be 0, the other to be 1. Doesn't really matter which one you pick, and we can work with that. So that's easy. But what about, let's say you are buying a car. Manufacturer has many different possible colors. They often have 10, 12 colors. How do we represent that? Now, I don't have, let's say the manufacturer has, 15 colors. Well, we don't have a 15-state computer. Our computers are designed to be binary. Or let's say I have measuring the temperature in this room using a thermostat. There's a temperature sensor. It measures the temperature. It discretizes it, perhaps let's say to the nearest degree Fahrenheit. The temperature in this room, LA, probably can range from let's say 40 degree to let's say 100 degree. So I have 60 different values. I need to represent those. My computer is not 60, doesn't have 60 distinct states. So I have to somehow create that. So any suggestion, how would we do that? So let's take the example of car colors, 15 colors. My computer can deal with bits. How would you represent? Go ahead. Use more bits. Okay, so how many bits will you use? 4. Can anyone explain why 4? Yeah, so 2 to the power 4 is the smallest power of 2 greater than what I'm trying to represent. Or alternatively, log to the base 2 of 15, as you were saying, with a ceiling. You have to take the next higher number to that. That's one possible way of representing it. So actually, we need at least 4 bits, right? I can also take, let's say, a vector of 15 bits, position number 1 for color number 1, position number 2 for color number 2, and so on and so forth. In which case, I have a very wasteful representation, but it's a valid representation. So I have many different possibilities, but so 4 is the minimum number of bits I need, but I could certainly represent it more wastefully if I so choose to. So that's the color example, 8 colors in this case. We use multiple bits. This is an example. Yeah, in this case, 8 colors, 3 bits. I use all the possible 3-bit combinations. Which one I assign to which doesn't really matter, as long as there is a unique mapping that I am able to establish. But I could use more bits if I so choose also. So if I have n bits, I can represent 2 to the power n distinct things. So that's why we get the log to the base 2 in the reverse direction. Minimum number of bits to represent m distinct elements is, so let's write it down. This is to the power n, and this is going to be log to the base 2 of m, and then ceiling. That many minimum number of bits that we are going to need. Is this not clear to anyone? Okay. Now, let's talk about how do we represent continuous information with binary signals. So my thermostat example, let's say my thermostat is going to see readings, temperature from 68 to 82 degrees, and we need it to an accuracy of 2 degrees Fahrenheit. How would we represent it? So immediately you can see that if I'm trying to represent continuous valued things, I have to establish some resolution of it, because between 16 and 82, there are infinite many temperatures. I cannot represent them all. So I have to discretize. And very common one is we pick a uniform resolution. We say, I'm interested in temperature close to a 2 degree accuracy. So if I have 68 to 82, then I have possible values are 68, 70, 72, all the way to 82. And the question then becomes, how do we represent it? So again, I have a table like this. So once we discretize the continuous range, I'm down to my original problem. In this case, I have 8 possible values. So how many bits would I need? Anyone? How many bits? 3, right? At least. So I could do this mapping. And again, that mapping doesn't have to be this particular one. Here I made 68 to be 0, 0, 0. You may make a choice that, oh, 0, 0, 0 is 80. I mean, again, it's the one-to-one mapping that matters, not which bit is assigned to which number. Having said that, not all mappings are equivalent. It may turn out for what you need to do, it's a lot easier to have one mapping versus another. So let's take this example. I chose the mapping where I assigned the temperature and the binary encoding in the same increasing order. So the lowest temperature has the lowest binary number. If I were to think of 000, it's the number 0. 70 has the next binary number, 1, and so on and so forth. So they are both increasing the same way. And as you can imagine, this might make certain operations easy. If I were to ask you, which temperature is greater, 101 or 001? In this case, it's very easy because you can say binary number 101 is greater than binary number 001, therefore the corresponding temperature must be greater. If I had some other random mapping, then that simple operation may require a lot more complicated algorithm to do that. So to emphasize the point, mapping could be arbitrary, but not all mappings are the same. So going back out here, how many distinct 3-bit mappings exist for this problem? So I have 8 temperatures. I'm going to use 3 bits. How many different mappings exist? Like for example, this is one mapping. Another one is maybe I just go in the reverse direction. So there are many other possibilities. So how many distinct possibilities are there? 8 factorial. So first one 8, next choice 7, and so on and so forth. Okay. So there are 8 factorial possible mappings. Pretty large number. Some of them are going to be good for a particular application. Some may not be. When you're dealing with numbers, it's very common to assign them in rising or falling order. But if you are dealing with like colors and stuff like that, maybe no particular mapping is particularly good or bad. Okay, so in electronic systems, that task of going from that continuous temperature to these numbers is done using a special circuit called analog to digital converter, ADC. And good ADCs are very critical because they are basically sitting at the edges of our computers. They monitor the physical world, continuously digitize readings from a sensor or some such thing, and then the computer takes over and manipulates them. So design of ADCs which are fast, have many bits, are reliable, can operate with consuming low energy and all. It's a serious research area on its own. As you can imagine, what's happening out here is the circuit has to sample the continuous signal, let's say a temperature or something like that, and then convert it into find the nearest digital mapping for it and output that. So turns out to be a reasonably tricky thing to do, and particularly if you're doing it very fast. And progress in that in large measure is what has enabled a lot of technologies that you see around us, particularly like high resolution video, high quality sound. All of these things became possible as we figured out how to digitize things very rapidly and with a large number of bits. So ADCs get used for that. Multiple ways to represent information. So it's a point we have already made. So again, in our particular example, this is the mapping we had used for thermostat temperature, but I could have used a different mapping. In this case, I'm using 7 bits to map the different temperature values. This is an equally valid mapping. In this case also, I can figure out which temperature is larger or smaller by counting the number of ones, for example. So it has some intriguing property also. Now, 7 is more than the minimum number needed. So this is what is called as a redundant coding. I have more bits than what were truly essential. So this is redundant coding because I'm using more bits than necessary. Another very commonly used representation is I use as many bits as I have the number of as the number of discrete values I have. So in this case, we have 8 values. So we are going to use 8 bits. And then whichever value I have is indicated by a 1 in the corresponding position. So like, for example, 68 means position, leftmost position is 1, the rest are 0. 70 means the second bit is 1, others are 0, and so forth. It turns out this kind of circuit also makes certain operations very easy. But the disadvantage is that I need, instead of log 2 n bits, I need n bits. So it can be very wasteful in terms of cost of storage or cost of communicating the bits across some distance. But it can make some operations very, very easy. So main moral of the story out here is that there is no one unique way to represent information. In fact, each one of these representation may find some use in some system because it makes some operation particularly easy. So let's consider some example. A date, days since January 1st, 0000. How many bits do you think we'll need? Rough estimate, quick and dirty type estimate. 18. No. I had the luxury of solving it beforehand, so. But how would you approach it? Let's put it this way. So instead of giving me the actual number, how would you approach this problem? Go ahead.
365 times to the 14 plus like 3 days and then log is 2 then.
Good. And it will turn out to be like 19.5 or something like that, and which is why it's 20. And that will keep us good till for another 1,000 years or so. But absolutely. So that's what it is. Okay. Next one. Let's say I want to represent a date as month, day, and year. So this is an alternative way of representing date, right? The first one was valid. The next one is I'm going to think of a date as having 3 fields: month field, day field, and a year field. How many bits will we need now? So how many bits for month? 4. How many for day in the month? So how many bits so 31 days, how many bits do we need? 5. And year, let's say we are sticking with 4-digit years, so you can work it out. Okay. Month, day, year, day of week. So now I need the previous ones plus day of week, 7 days. I need another 3 bits. So I need 24 bits. Now, how would you compare the second and third? I mean, second was sufficient to represent a day uniquely. So the third option, where I'm also listing the day of the week, actually has redundant information in it, right? I can always calculate day of the week given month, day, and year. So in this case, day of the week is actually redundant information, but for certain operations, it may be easy for us to carry that information along so that I don't have to compute it. So oftentimes you would see in our digital systems, what we do is we carry information where instead of computing it when I need it, I pre-compute it and then carry along with me. So in this particular case, we decided that we'll carry along day of the week. We could have computed it whenever we needed it, but makes life easier to have it with us all the time. So this is an example of a redundant representation where my data structure has a field which I truly didn't need, but it may be helpful for simplifying my application. Okay, let's take a playing card deck. I could represent a playing card as a number in the deck, in which case 52 cards, so I need 6 bits. if I decide to represent the card as a suit plus number, how many bits do I need? So 4 suits, I need 2 bits, 13, another 4 bits. So here also, again, I need 6 bits. But the coding would be different in this case, right? I mean, if I were to, even though both are using 6 bits, a mapping that a particular card would have, the bit pattern would look different in the 2 codings. How about decoded suit and decoded numbers? In this case, what it means is one hot coding. So I'll have 4 bit plus 13 bits, 17 bits. This is using excessive number of bits, but maybe easier for doing some operations. 5 card hand. So let's say you are playing poker and you draw a 5 card hand, 5 cards. How many bits do you need to represent the hand? So firstly, how many hands are there? How many 5 card hands are there out of a deck? Anyone? Try to, okay, go ahead. 52C5. So it's factorial 52 over factorial 5 and factorial 47. Okay, so that many distinct cards. So this is your whatever high school permutation combination kind of thing, right? And the logic behind this thing is, those of you have forgotten, the first card I can draw 52 ways. Next card I can draw 51 ways, 50, 49, 48. But then the order doesn't matter in this case. So I have to divide by the number of permutations that may exist within the hand. So that would be factorial 5. So that's why we end up with n 52 choose 5. And in this case, that's kind of a magical number. And you can calculate the log 2 of that, turns out to be 22 bits. So I need 22 bits at least to represent all possible 5 card hands which exist. So how would we select a representation? So main things that we learned, there is no unique representation. All we can certainly tell is how many minimum number of bits I need. But there is no unique representation. Representation may depend upon what you want to do with it. So the decision as to which representation is better depends upon what you need to do with it, what operations you need to do on that. So let's take an example. Let's say, so go back to this thing, I'm representing day of the year. And there are many possibilities of that representation, and there are many possible operations. So let's imagine I'm making a system which has to do these operations. It has to find, given the representation for today, it has to find the representation for tomorrow. That's one operation. Another operation we want to do is, you give me 2 days of the year in their binary representation, and I want the system to tell me whether they are in the same month. A third operation we want to do is, given 2 representation, I want to tell you whether day 1 is before or after day 2 in the year. And the final one we want to do is, I want to, given the representation of a day, I want the system to tell me whether which day of the week is it. Is it Thursday or is it Tuesday? Now let's look at various possibilities. So let's say we decide to represent day of the year as a 9-bit number, 1 through 365 or 366. Determining representation of tomorrow, is that easy or hard? Easy, just increment by 1. What about determining if 2 days are in the same month? So I give you 2 numbers, whatever, 53 and 53 and 59, are they in the same month? Well, I mean, it's not that easy because it may straddle 2 months. If they are more than 31 apart, you know for sure they are in different months. Otherwise, you'll have to worry about which month, whether they are in the same month or not. So it's not an easy operation, as you can imagine. In this, when I'm representing things this way. Determine if a day comes before or after another. It's easy, it's just a comparison. And finally, determine if the day is a particular day of the week. Again, hard, you have to kind of also, I'm assuming you know what day of the week was January 1st, and then you'll have to do some modulo 7 kind of operation to get things out. So it's not easy. Let's take another representation. I represent the day now as a month plus day of the month. Okay. So now I have to, which operations become easy with this one? So if I'm representing a day as a month field and a day of the month field. So are any of these operations now made easier? Second one is easier. Determine if 2 days are in the same month. I just compare the month field. Determine if one day comes before another. You'll compare the month. If the month is the same, you are going to compare the day, right? So that's how it will work. Determine if a day is a particular day of the week. It actually remains hard. It's probably even harder now. Determine representation of tomorrow. I increment the day, and if it goes beyond, it's kind of a hard operation because you have to worry about which month it is and all. So easy. Hard, I guess the first one is kind of what I would put as a medium category out here. Last one, I do month, day of the month, day of the week. Now, all operations become easy in this particular case, but I'm using more bits. So sometimes by throwing more bits at the problem, you can make operations easier, and that may kind of dictate your choices. So it depends on what operation you are doing. That's kind of what one needs to think about. Going back to something that we started out with, that little, when we were representing values in terms of voltages, and we had this middle region which I had put a question mark on, and the question was, what is that doing? What purpose does it serve? Well, the main thing really out here is to deal with noise. So remember, our underlying stuff is analog. So let's say I have an input, which is a voltage. But when voltages travel over wire, they pick up noise from AC line, from radio signals and whatnot. So what my system sees is not the real value, but by the time it reaches it, it has some noise added to it. So it has been perturbed. So instead of seeing V, I may be seeing V plus something or V minus something, hopefully some tiny value. And that's what reaches my digital system. What my digital system will produce is not f of V, but rather f of that V plus noise added to it. And now I have an output, and there would be error at that output. So in a normal analog system, what happens is this FV plus E, V plus error, is not the same as f of V. There is noise in the output. So whereas in a digital system, what happens is somehow magically, digital system self-corrects. So if instead of outputting the value corresponding to voltage plus error, it actually will figure out a way of outputting the correct value. And what it comes from is, as we'll see, that there is a property that digital systems have, which is they're designed so that these errors are eliminated. And the way it works is the following. We will design our digital system so that whenever it outputs a 0, so remember, our 0 was this entire range. We were okay with this entire range being 0. But we'll design our digital system so that whenever they output a 0, they are going to output over a narrower range, this particular range. As you can see, this lower range is a subset of all the voltage which we are willing to consider as 0. So the advantage out here is my digital system is always going to output a tighter range of voltages. And now if some noise get added to it, either negative noise or positive noise, there's a high likelihood I will still remain in the 0 range, right? I mean, for this guy, if the output was this, for it to be not considered a 0, I will have to add noise which corresponds to this voltage. And this is what we call as VNML, or noise margin for the low side. So it's basically saying that my system may have noise, may pick up noise, electrical noise, but as long as the noise is less than VNML, then a 0 will still be treated as a 0 by the whatever other system is reading it. So digital systems on the input side are more lax. They consider a wider range of values to be 0 and a wider range of values to be 1. But whenever they output, they are designed so that they output a tinier range of values, voltages. And then even when noise gets added to them, they will still be considered as 0. Same game is being played out here, if you would. So our 1 was this broader range on the input side, but when we are outputting a 1, we are outputting it over a much tighter range. So for example, on the input side, I may say any voltage from 3 to 5 volt is a 1. But whenever I'm outputting, I will make sure I output only, let's say, 3.75 to 4.25. And in that case, even if I get 0.75 voltage of noise, I will still be in the range of 1 and therefore be okay. So what you see out here is this VNMH, which is the high noise margin. It's basically saying how much the voltage value for 1 can be perturbed, and I will still think of it as a 1. Okay, and it's this property, is these noise margins, which make digital systems very robust. In an analog system, the noise manifests itself on the output, whereas in a digital system, it gets ignored because the next stage is going to still think of it as a 1, even though the noise was added to that. So it's a very powerful property, which is what makes, like, normally associate digital stuff with higher quality, because it basically has less noise. When, for example, CD-ROMs came out, all of you are too young, but like when it first came out in 80s, before that we used to have these LP records, which were analog systems, a needle tracking the groove on those LP records. Every little noise and dust particle was picked up and you could hear on the speaker. With the CDs, there are zeros and ones written in the disc, and even though there may be a scratch or stuff like that, it gets ignored because through processing and all, we kind of manage to ignore that. So the digital sound is a lot cleaner. So, and it kind of owes it back to this, that noise is suppressed in a digital system. Not all noise. Clearly, if my noise was higher than my noise margin, then my 0 may become 1 or 1 may become 0. But a lot of noise can be ignored this particular way. Any questions on this? This is sort of probably the only electrical stuff we are going to see in this course. But it's an important concept as to why digital. Why did we not stick with analog? It's this reliability that we get. Any questions on this? Okay, so TAs will go through an example of this to work out the noise margins. Okay, so this property is called restoration of digital signal. So what's happening is that in an analog system, as noise gets added, it accumulates. So every time noise gets added, by the time I see the output, I'm seeing kind of a larger and larger and larger noise. In the digital system, on the other hand, every time, so as you see, this little symbol is a type of digital system. And what you would see is that even though input had some noise, the output is still the clean signal. And likewise, again, noise got added, but again, the digital system ignored it because of that property, that some amount of noise still leaves a signal at the right logic value, even though voltage value changed. So that's a powerful property. And one way of thinking about the way these digital systems are being done is that what you would see is that on the input side, they are looking at a larger range of values to be a 0, and this large range of value to be a 1. On the output side, a much smaller range of value is 1 and a much smaller range of value is 0. So output are tightly controlled, input are more relaxed. Now a question which comes up is, or should come to your mind is, why am I not outputting just a single value for the output voltage? Or why am I not outputting a single value for 0 and a single value for 1? Any thoughts? Like, why am I still showing a little band of values for 1 and a little band of values for 0 on the output side? Why not a single voltage, 4.0 volt for output 1 and let's say 1.0 volt for output logic 0? Why do I have a band there? Any speculation? Let's take an analogy. Let's say you are machining a part. You go to the mechanical engineering lab and you are supposed to make a 1-inch cube. Do you think you will be able to make a 1-inch cube exactly 1 inch by 1 inch by 1 inch? No. What comes in the way? Manufacturing error, right? I mean, there are machines that have tolerances and all, right? So when I make digital systems, when I make the transistors in an electronic digital system, these things are things drawn on silicon. They're drawn using light and all. So when I'm drawing these things and then I'm changing their electrical properties by putting chemicals in them, all of these things are manufacturing processes. So every time I make a computer chip, when I make another instance of it, it is different somewhat. And third copy would be yet other different. So when I take identical part numbers from Intel and run them together and I feed them the same input voltage and keep them in the same temperature, the output voltage still will vary. So what you are seeing out here, the spread is essential because that gives us some tolerance that my manufacturing could still be off, or maybe my room temperature may be a little bit different and whatnot, but my system would still work. Okay, so it's important, this kind of variation that we are seeing is to basically be realistic that you are designing, whenever you engineer a system, whenever you make a system, it's going to have some errors, it's going to have some manufacturing related tolerances, and that's what it's accounting for. So this part is tolerance to manufacturing. And so it's just part and parcel of life. Deep down, these electrical systems are essentially made using chemicals and mechanical drawing, and also we still have to kind of deal with that. Okay, so that closes this particular module. The next one we are going to start on how do we process these things? So what we have seen thus far is how to represent information. Now what we're going to talk about is how do we process this information. Okay, this is still chapter 1. So now when we process digital information, the simplest kind of digital system that you can imagine is what is called as combinational logic system or combinational logic circuit. And what these things are is they are basically like a mathematical function. They take an input and they give you a mapping, they map it to an output. So for example, let's say I'm designing a thermostat which is going to take a temperature from a sensor, current temperature. Let's say it has 4 possible values, so 2 bits. It will also take a preset temperature. All thermostats let you set too hot or too cold, some sort of threshold temperature. So we have the preset temperature. And then I want to make a circuit, a system, which is going to compare the 2 values. And then it's going to output a signal 1 or 0. 1 if A is greater than B, 0 if A is less than equal to B. And if current temperature is greater than preset temperature, then output is 1, and that we will feed it to a fan to turn it on. So what's happening in the system is, as preset temperature is hopefully fixed once the user sets it, current temperature is changing. As the current temperature is changing, the fan will come on or off depending upon whether the current temperature is higher or lower than the preset temperature. So in this case, all we are doing is we are taking these two 2-bit numbers, and at any instant in time, my output is either 1 or 0 depending upon their relative value. So that's an example of a combinational system, because one way of thinking about combinational system, it has no memory. All it is doing is at the current point in time, it computes a mathematical function over its inputs, and then it just outputs that. So in our particular case, let's say the temperatures could be 50, 60, 70, 80, and we decide to map them to 0, 0, 0, 1, 1, 0, 1, 1, and likewise for preset, let's say I have 4 values, and again I map them the same way. I can make a table where I can list all the current temperature, and then for each current temperature, I can list all possible values of the preset temperature. So like, for example, my current may be 50, preset may be 60, current may be 50, preset may be 65, 50, 70, 50, 75, and so on and so forth. So I have 16 possible combinations that may exist, and for each one of them, I can see whether the fan A is greater than B or not. So that is easy to do. First one, A is less than B, so output is no, no, and so on and so forth. So I'll kind of what you can see is that wherever I have a Y, that's where we want the fan to be on. Wherever I have an N, the current temperature is lower than the preset, I don't want the fan to be on. Now this is the logic of my problem. I can convert it into binary representation in terms of binary coding. So I list down current temperature and preset temperature in terms of the mappings that we have listed out here. So like 50 is 0, 0, and for current temperature, and likewise the preset temperature of 60 is also 0, 0. So my first mapping is 0, 0, 0, 0, and the output is 0. Can someone help me with the second one? What would the second row look like? So tell me, so what should I put in the second row, first column? Oh. 0, 0. So 0, 1, and output should be 0, right? And I can kind of fill the table out this way, right? So, which I have already done, so I'm not going to. Okay, so I have filled out that table. It's literally just a one-to-one mapping of the left table. And this table is called as the truth table. It is basically describing a binary function. Its inputs are represented in bits. It has a single 1-bit output, and those are also represented in bits. And this is what is called as a truth table. What combinational digital systems do is they basically represent these truth tables. Now let's say I were to remove one of the possibilities of preset temperature. Thus far, previously I had a 75 also, but now I have removed the 75. So if I now look at my table, the combinations corresponding to preset temperature of 75 are no more there. So this table has 12 entries as opposed to 16. And I can make the corresponding binary table in terms of bits. It would look like what we have out there. But now, when I design this system and I feed it the input, there are certain binary patterns for which the table doesn't say what to do. So for example, if my input is 0, 0, 1, 1, the table does not tell me what to do. Likewise, if my input is 0, 1, 1, 1, Again, the table does not tell me what to do. What do you think should happen? So I made this system. If I now I have this electrical system, I can feed input to it. So nothing stops me from feeding a 1-1 for the preset temperature, even though the table doesn't have that entry for it. So what should the system do? So I guess let's say you're designing the system, and this is the spec I gave you. You created the system, and now I actually fed preset to be 1-1, which didn't occur out here. As a reasonable engineer, what do you think a system should do? A reasonably engineered system. Okay, so you could disregard it, was some comment. What does that mean? What does disregard mean? Fan on, fan off, what? Huh? Fan stays at whatever, okay. So those are all reasonable possibilities. What else could you do? What else? Crash or whatever. Put an error message, right? Crash is not a good thing, but putting an error message might be a reasonable thing to do. Or another possibility is that you may say that, it's unpredictable if input is out of the spec. I can do whichever, fan may be on or off. So these things are often encountered, and a very common way of dealing with them is to say, this is out of spec, it should never occur, we don't care. As a designer, we are going to choose whatever makes my design more efficient. Okay, so that could be one answer to take, in which case we just call them as don't cares. So you will see truth tables where some entries may have a D or an X or a dash, which stands for don't care. Okay, that is, what don't care means is that depending upon my design, I may either make it a 0 or a 1. I as a designer, I will retain that flexibility for myself. Okay. So my new truth table looks like this. Now I have some entries which have a don't care on it, and I will assign them to be assign a don't care to be a 0 or a 1 based upon something that I as a designer would do. Maybe it will reduce the cost of my design. Maybe the design will consume less power. Could be any reason like that. We'll see later in the course what implications it has. Okay, so combinational logic are memoryless. That is, at any instant in time, they take the input, map it to the output. If I change the input, the output immediately changes. They literally are a mathematical function. Every time the input changes, as soon as the input changes, the output changes. And in an ideal sense, they change instantaneously. In a real circuit, perhaps after a few nanoseconds of delay. But the output follows the input. These are memoryless because they don't know anything about the history. Like, at any given time, I don't care what the previous inputs were. All I do is I make sure I compute the new output corresponding to the new input. But now let's imagine I'm trying to make a digital calendar. So I want to show that how combinational logic is not always enough. So I can design a computer. I can design a logic which can compute tomorrow. So it can take my input representation, in which case the input representation is month, day of month, and day of week, and it can always compute the tomorrow. So through some mapping, you can imagine a gigantic truth table, and it is going to implement that. So that part is easy. I can design the combination logic, but a digital calendar at midnight should move to tomorrow, right? So I have today, I can compute tomorrow, and at midnight, I want to shift it. I make the output to be tomorrow, but not at other times. So the way one could do something like this is to introduce a special circuit block, which is this cyan colored thing, and it has the signal at the bottom, midnight. This block is a special one. Its input may keep changing. The output will not change unless midnight is high. So what we'll do is at midnight, for a tiny period of time, I'm going to make midnight to be high, logic 1. And then that cyan block will take its input and put it on its output. And then I'm going to pull down the midnight, and then rest of the day, the output will remain unchanged. This compute tomorrow is what it's doing is it's just adding 1 to the representation of the day. So it's a purely combinational thing. The output here immediately follows. So the output here immediately follows whatever is happening. Whenever this guy changes, the left guy, this guy immediately changes on the right. But this one changes, the output changes only when midnight comes. At midnight, the output of the cyan block will copy whatever is on its input. At other times, the output just remembers whatever it was thus far. It holds its value. And this is no longer a truth table, right? I mean, here something is happening at a special point in time. Otherwise, it's remembering the value. It is holding the value since the last midnight tick. At midnight, a tick comes, I get a new value, and then I'll keep outputting that old value until the next midnight. So it has kind of a memory in it. It remembers what happened at the latest midnight tick. And this kind of circuit requires us to go beyond combinational logic. It has memory. It can store bits. And the latter part of the course is going to deal with this, but it's a weird circuit. It's much more complicated. It has memory, and it takes this funny input, a tick, which is the midnight tick, which is kind of like which is something I referred to earlier as clock. So we'll see much of this starting maybe like week 6 or so. The special circuit is called a register. So a register is a digital logic block which remembers the value, and the value it outputs is whatever is the content of the register, and the content of the register is updated whenever that clock comes. In our example, midnight was the clock. So every time there is midnight, the input is read and stored into the register. At all other time, the output of the register is simply whatever is stored in the register. If you think about it, our memories in our computer are exactly these. They're just a whole bunch of registers. So when you look at the DRAM or flash memory or disk and all, they're basically kind of acting as this kind of a device that you can write to them at certain point in time, but otherwise whenever you read them, they have whatever was last written into them. And last written into them was whenever the clock came. So this is a weird circuit, and we kind of, our digital calendar has both. It has the combinational part and it has the digital part. Final thing, let's see, how much time do I have? I have 2 minutes. The TAs will pick this example up again, but basically I can represent, you'll see in the discussion section, we can represent these combinational circuits using simpler things called gates. And you see these two funny symbols, AND gate and NOT gate. And a NOT gate is a special digital system whose output is the opposite of its input. So if the input is 1, output is 0. If the input is 0, output is 1. AND gate is another special circuit which outputs 1 when both the inputs are 1. Otherwise, it outputs a 0. And there are other such circuits. Let's see. Other such circuits, and again, the TAs will go over it. And we make more complicated circuits by stitching them together. So I'm going to stop at this stage. Again, please remember, no lecture on Wednesday. And you need to go through homework 1 and submit it by Friday morning.